Welcome back to DATQVAULT video lectures. In this video we're going to cover first order substitution reactions. So substitution reactions are pretty much exactly what they sound like. In a substitution reaction we're going to have some sort of substrate that has a good leaving group on it, which is represented by Lg. And then we're going to have some sort of a good nucleophile which has a lone pair of electrons and is usually negatively charged. In a substitution reaction, we're just going to take the nucleophile and we attack the substrate in such a way that it pushes off the leaving group, and we substitute the nucleophile for the leaving group. And it's pretty much as easy as that. There are two different types of substitution mechanisms. There is an SN1 substitution mechanism. SN1 stands for substitution, the N stands for nucleophilic, and then the 1 stands for first order. We're going to understand what first order means in the kinetics a little bit later on in the lecture. In an SN1 style mechanism, we form a carbocation intermediate. This goes along with the reaction being first order. Because we form a carbocation intermediate in an SN1 reaction, that means secondary and tertiary carbons are the only types of carbons that can undergo an SN1 mechanism, because we need to form a stable carbocation. Also, SN1 reactions are not stereospecific reactions, which means that the stereochemistry in the reaction is not retained. And we'll go over why this is a little bit later. The other type of substitution reaction is an SN2 style substitution reaction. Again, S stands for substitution, N stands for the reaction being nucleophilic, and then the 2 standing for second order. In a second order substitution mechanism, there is no carbocation intermediate formed. This is because the reaction is second order in nature. Because there is no carbocation formed, only primary carbons undergo SN2 style substitutions, and these substitutions are stereospecific, and they're stereospecific because they go through an inversion of stereochemistry. In this lecture we're going to specifically focus on SN1 style substitutions, and there will be another lecture on SN2 style substitutions as well. Alright, so what does the reaction mechanism look like for an SN style substitution, SN1 style substitution? Because a carbocation is formed, the first step is the leaving group leaves off of the substrate and we form the carbocation. Because we're forming a carbocation, the only substrates that are allowed to undergo an SN1 reaction mechanism are secondary and tertiary carbons. If we had a primary carbon with a leaving group leave, we'd form a primary carbocation, and we know that primary carbocations are not very stable. So substrate has to be secondary or tertiary around the carbon, and then the leaving group has a few distinct properties as well. On a DAT, you're most likely to see the leaving group being some sort of a halide. One important thing to remember about the leaving group, and if it's a halide, is the rate at which different halides leave to form this carbocation. The larger the halide, iodine being the largest, fluorine being the smallest, the reaction rate is going to increase for the larger halides. This is because once the leaving group leaves, it's going to be bearing a negative charge. Larger atoms, such as iodine, are more polarizable, and they can stabilize this negative charge better than smaller halides such as fluorine and chlorine. So the larger the halide for a leaving group, the faster you're going to form the carbocation, and the faster the substitution reaction is going to proceed. Alright, so in an SN1 style reaction mechanism, the first step is to form your carbocation intermediate. And then the next step is the nucleophile comes in and attacks the carbocation. Once this happens, we get our substitution to occur. The nucleophile is then attached to the carbon. The leaving group leaves. But what does this tell us about the stereochemistry of the overall reaction? I told you a little bit earlier that the stereochemistry is not retained and the reaction is not stereospecific. But what does this exactly mean? So first we had to understand what a carbocation exactly looks like when we form it. So carbocations, one of them is represented here with 3 different substituents attached to the carbon, the central carbon, which bears the positive charge. Carbocations are sp2 hybridized, which means they are planar. And then there is an empty p orbital here represented by these 2 empty lobes with a positive charge, of course. So, like I said up here above, the nucleophile then comes in and will attack this empty p orbital. So, remember, p orbitals can be attacked from either side. If the p orbital is attacked from the top side, we will get stereochemistry that looks like this. If our nucleophile attacks the p orbital from the bottom side, all the substituents get pushed upwards, and we get stereochemistry around the central carbon that looks like this. So what if our substrate has a specific stereochemistry, which means there are 4 different substituents attached to the initial substrate, and let's say it bears a certain stereochemistry. There is a single enantiomer for our starting material. Once the leaving group on the starting material leaves and we form this carbocation, the nucleophile can then attack either lobe of the empty p orbital, and we will get then a mixture of 2 different enantiomers. So if we start with a single enantiomer and the reaction undergoes an SN1 style reaction mechanism, we then get a mixture of 2 different enantiomers, and the stereochemistry is not retained. So we go from 1 enantiomer to 2 different enantiomers, so we completely destroy the stereochemistry around the central carbon. This is a very important thing to know about the SN1 style reaction mechanism. Alright, so what do the kinetics look like of an SN style reaction? This is going to be very important for the DAT. I cannot emphasize how important it is to know the kinetics of these types of reactions and how these questions pop up all the time on the exam. So here on the x-axis we have energy, and down here, on the x-axis we have the reaction coordinate, y-axis we have energy. So here is our starting material. It has some sort of energy level. Here we just have a bromide as the leaving group, surrounded by a tertiary carbon. So this substrate, if it undergoes a substitution reaction mechanism, will go under an SN1 style reaction mechanism. So the first step in the mechanism is this bromide is going to leave. So we're going to break the carbon halogen bond, or the carbon leaving group bond. So when this happens, we get a much higher energy state for the bond being broken. So we draw a line up to this energy state, and then once the bond is fully broken, we form our carbocation intermediate, and we form a negatively charged halide. So this is the first step in the reaction mechanism, is the formation of the carbocation intermediate. This is very important for the SN1 style reaction mechanism. And remember when I said SN1 style, the 1 stands for first order, which means it's a unimolecular reaction. So in the formation of the first intermediate in this reaction, we're only using 1 single molecule, which is the starting material. So the second step in the SN1 mechanism is for some sort of a nucleophile to attack the carbocation. In this case, our nucleophile is going to be a hydroxide. So the formation of the bond takes some sort of energy, and then once the bond is fully formed, our product is going to be much lower in energy than our starting material. So what is the rate constant, or what does the rate of the overall reaction look like? K being some sort of a rate constant based on factors like solvents and the how good the leaving group is, and then the concentration of only the substrate and not the nucleophile. This is because the formation of the intermediate, the rate limiting step, because this is the largest energy barrier right here, only involves the starting material. Alright, so let's answer a question about substitution kinetics of an SN1 style mechanism. So why don't you go ahead and pause the video for a second, try to answer this question, and then we'll go over it together. Alright, so this question asks what's true about a first order substitution reaction? So we just went over the kinetics, and we should be able to answer this question pretty easily. Alright, so I just do elimination of these three different choices. Let's go over the first possible answer. Says a first order substitution reaction mechanism is going to be a bimolecular reaction. So first order means unimolecular. So only one molecule is involved in the rate limiting step of the reaction. So the reaction cannot be bimolecular because it's first order, so that answer is completely false. So the second choice is the carbocation formation is rate limiting. So if we remember the diagram that I showed you before, the rate limiting step, which is the step that has the highest energy barrier, is going to be indeed the formation of the carbocation. So the step with the highest energy barrier is the rate limiting step. So the formation of the carbocation is rate limiting, so this is true. Alright, so the third choice is the reaction depends on nucleophile concentration. Since the reaction is first order and is unimolecular, the concentration of the nucleophile does not matter whatsoever. Only the concentration of the substrate matters. So answer 3 is going to be false. So 2 is our only correct answer in this question. Alright, so because SN1 style reaction mechanisms go through a carbocation intermediate, we can get carbocation rearrangements. So in the reaction mechanism, the first step is for the halogen to leave and then for the nucleophile to come in and attack the carbocation. If our nucleophile, in this case methanol, comes in and attacks our first carbocation formed here, then we're going to get this substitution as our product. But so has it that there is an alpha hydrogen here on this carbocation intermediate that can do a hydride shift over to our carbocation to form a more stable tertiary carbocation. This is going to happen much faster than the attack of the nucleophile, in this case methanol. So once methanol attacks this tertiary carbon here, we're going to get much more stable tertiary substitution. So this is going to be our major product, and this product is going to end up being a minor product. So because a carbocation is formed, remember, we have to always look out for possible hydride shifts or methyl shifts to form more stable carbocations. Alright, so here we're being asked what the most stable intermediate is for the following reaction. So why don't you take a second and try to answer this problem, and then we'll go over it together. Alright, so intermediates are common questions that are asked on the DAT. So if we're forming an intermediate from this reaction, we're going to assume that it's going to be some sort of a substitution reaction. In this case, we need to be able to recognize that we have a secondary carbon here, and then we have a halide, which is a relatively good leaving group. So this halide leaves, the intermediate that we get immediately is going to be a secondary carbocation. So since we form a carbocation in this reaction, We need to look out for hydride shifts or carbocation rearrangements. Here we have an adjacent hydrogen to this carbocation that, if it shifts over to this carbocation, we form a more stable tertiary carbocation. So out of the top 4 choices, we see that we have a tertiary carbocation right here, which is going to be our most stable intermediate. E is actually not an intermediate, it's a product, and it's actually the elimination product of this hydrogen right here. This doesn't happen because methanol is not a strong enough base for the deprotonation, and that's why we get the substitution instead. Alright, so this is an overview on SN1 style mechanisms. So why don't you go ahead and either take a quiz or answer some problems on SN1 style substitutions or substitution reactions in general to solidify everything that we covered in this lecture.